The title of the talk is Right Said Fred. The Fred in question is good old Fred Hoyle, who I'm sure lots of you are well aware of. What Fred came up with was he postulated, he guessed there had to be a coincidence between two nuclear arrangements, else we couldn't get an interesting universe. Now, what makes our universe particularly interesting? We've got wonderful things in there that the society is certainly always well aware of. Magnetars, giant, supergiant black holes, etc., etc. But they're big, they're energetic, but they're nothing like as complex as what we've all got inside our heads. Those are by far, mammalian brains are by far the most complex things we know of. And how we make them is how the universe allows us to make them or get made is a crunch issue. How does it do it? It uses complex cellular structures, as you know, and that we arrive at them via this process of biological evolution. Biological evolution. What do you need to have biological evolution? You've got to have a rich suite of molecules for evolution to play with, put together in different ways, create life with them, create different sorts of life. And that's got to be repeatable. Information's got to be conveyed from one generation to the next with variation. We know all about all of that. The information's got to be reasonably stable and accessible, and the damn thing takes forever. So it's got to be stable for a long, long time. It's got to be very versatile. The chemistry of the interaction is really down to the chemistry of a much smaller suite. I mean, if you look at the molecules we have just here on Earth, it's a vast, vast number. But we make those molecules simply out of the combination of less than 100 entities, the atoms. They are, the vast richness is the combinatorial explosion of connecting these atoms in all the different ways that they can be connected. We have these different types of atoms and each type we label as an element. And the Earth is just host to 92 of these different elements. We probably don't need all of them to produce our brains, but that's what we've got. So out of these 92 different elements, they can combine to produce something that's as interesting as us. What do they need to do that? What allows atoms to support molecular evolution? They have to be able to provide the same chemistry. Each element has to be able to supply the same chemistry from one atom to another. And it's also got to do that over eons of time. So it's got to be reliable. You've got to know when your little E. coli decides he wants to use another carbon atom, he's got to make sure it's exactly the same as every carbon atom he's ever used. So how do they get so reliable? Atoms get reliable in their chemistry because the electrons enter reliably reproducible states. And it's the states of the electrons circulating the atoms that give us this reliability. The electrons spend most of their time in very few states. There's not a vast continuum of states for them to choose from when they're bound in an atom. There is, in theory, there's a countable infinity of them, but in practice, there's just a small number. And every life form knows exactly what it's dealing with. Each element, the atoms of the different elements, provide different suites of these dynamical states. So you have these 92 different ingredients for your palette from which you're going to construct ultimately biological evolution. As we say, it's an almost limitless landscape we get. So these electrons behaving in this highly constrained and reproducible manner, they're what provides this stable platform upon which evolution can produce all this wonderful stuff. Now, you know, when we thought about, when we realized these atoms were actually real, which is only really the end of the 19th century, and that we knew that they had electrons in and protons in, the only sensible way we could see they were organized would be in a mixture, with the protons well mixed in with the electrons, a sort of plasma ball. But when Rutherford came along with his co-workers and they began probing it, they found that it was like a solar system. They were using alpha particles, energetic, highly energetic alpha particles, firing them at a gold leaf packed with gold atoms, finding two great surprises. One, most of the alpha particles just went straight through, and two, the odd one would bounce straight back. Rutherford said it was like tossing a 15-inch shell at a piece of tissue paper and having it bounce back at you. They couldn't believe what this meant. What it meant was the atom was mostly empty space, that it had at the very center an extremely dense object that had all the positive charges in it. And the electrons, and we knew all about electrons, we got their weight, we knew how much charge they had. They were just floating around outside, like the planets. So very much in the system like planets. Charge on the proton is +1 in the appropriate units, and the charge on the electron is -1, exactly the same in magnitude, just opposite in sign. And this is a vital feature that, well, we still don't fully understand, but there we are. It is vital. And when we look at this nucleus, this tiny nucleus, the fact that it's packed with positive charge and that it's got most of the mass, you know, virtually each proton is each nucleon is 2,000 times, roughly 1,830 odd times heavier than an electron. It's tiny, it's enormously dense. And this is what enables the electrons to produce this reliable and reproducible behavior. It's this solar system structure. Now, is it just the fact that it's like a solar system? You can play a game and say, suppose we organized our solar system to be like an atom, and we could fiddle the nuclear physics so that the solar wind was huge. Planets would all acquire vast positive charge, leaving the sun with its a counterbalancing negative charge. And then we'd have something that looked very like an atom. We'd have a heavy central core of one charge and a bunch of light objects going round at a distance with the exact opposite charge. We could you know, do a model universe where all the planets were identical, like the electrons were all identical. Would we then be able to say, right, we could start linking up solar systems and end up with galactic life forms and have galactic evolution? And the answer is no, you can't. You can't do that. And the reason you can't do that is that no two solar systems, even given identical planets and an identical sun, no two would be alike, because the planets can occupy a continuous infinity of energies. They can, for any given energy, they can have a continuous variation in the ellipticity of their orbits, and also they're not stable. I mean, we think of the solar system as stable, but if you measure stability in terms of Lyapunov time, which is the time for it to become unpredictable to a factor E, then you get different times for different bits of the solar system, but on average, it's about 30 million years. Now, carbon atoms have been stable for many, many billions of years. No solar system would work like that. So therefore, your attempt at evolution would fail. So it's not that it's a solar system. Right, there we are. I go through that there. Oh yeah, I put that in. So it's not solely that it's that solar system organization. So what is it that gives us this well-defined, discrete set of states that we need to be repeatably well-defined enough to give us repeatable molecular configurations? One of the things it does is it confines the electrons to this tiny space. It's about 0.1 nanometers across. And when we get down to that size, we have systems that are dominated by quantum phase. And therefore, the only states that the electron will be generally found in is a one in which this phase, as it runs around the atom, constructively adds. You can think of this if you're not au fait with quantum phase, quantum mechanics. It is very, very strongly analogous to the way a musical instrument picks out particular notes. If you've got a string, you should be able to move the string around in any way you want, but if you tie the string at both ends and excite it, the only standing constructive waves that will happen will give you a reproducible pattern that you hear as the pitch of a note. There are other ways. If you pluck a guitar string, if you just recorded the first 100 milliseconds or so, a few hundred milliseconds, you would hear something that didn't sound like a musical note. What you'd be hearing is a transient set of phenomena, but they wipe themselves out. Their phases don't constructively add together, so they quickly wipe themselves out. In the way that if you disturb an electron in an atom, if I bring, say, another charged particle from outside the atom, I can disturb the electrons in the atom, but most of the disturbance will quickly wipe itself out. So we have this fleeting lifespan in musical instruments. We have fleeting lifespans of other states, but mostly it settles down to the notes. So when you play a piano, you hear a fixed set of notes. And you can think of the piano notes as being just a macroscopic analogy of the notes you would get from the electrons, the valence electrons in a carbon atom, and that would be different from those you would get in an oxygen atom, and so on. So size is critical there. And in fact, the analogy is so good that when we look at, say, the atomic orbital, the trajectories of an atom, of the electrons going around an atom, the maths is the maths that was developed way back in the end of the 18th century by Laplace for the vibrations of solids, where the standing vibrations were these constructive phase movements. So they're called spherical harmonics because he was dealing with things like bells and what have you. So the nucleus, because it's so dense, it drags them close in, and it will, if you've got a nucleus and you stick it in a sea of electrons, if you think of the very early first first second of the universe, you've got this hot plasma with stuff surging around. The nucleus will, as the plasma cools, it will automatically attract a number of electrons into those well-defined atomic states to form an atom. And we know, you all know that it does this. A hydrogen nucleus will do this, manages to do this once the universe has cooled enough that at something like 370,000 years. There'll be some, we'll see that there'll already be some helium nuclei. They'll do it earlier. They will grab the electrons after about 50,000 years. But the point is they will automatically grab the electrons until there's just as many electrons circulating as there are protons on the nucleus. Because whilst there are more protons, then there is an attraction. You've got to remember that, you know, the positive charges of the protons attract the negative charge of the electron. Opposites attract in electromagnetism. So it will keep on attracting them until there's an equal balance, after which any electron passing generally in the vicinity won't feel an attraction, because the repulsive negative charges on the electrons will cancel the attractive charge of the proton. So once you've got a nucleus with a few protons on, you will produce, once the universe is cool enough, you will automatically produce your atom. So the trick is to get a number of protons. If you want a number of different atoms, if you don't want it all to be just hydrogen, then you've got to get a number of protons to stick together. So this question, what's the single most important feature our universe has once it's created a space-time that is big, you know, and that's, I suppose we have to say, that is the most interesting feature, that it's big. I always remember the opening thing of Hitchhiker's Guide to the Galaxy, where Douglas Adams says, you may think that the distance down to the chemist shop is big, but it's peanuts to space. And that's basically what we've got to play with. So we've got a nice amount of space to play with. But the single most vital thing that it has to do, if we're going to get interesting things in this space, is to populate it with nuclei which have different number of protons. And these protons have got to stick very, very close together. Once they've done that, in the end, we'll have we'll get rocks, rabbits, and rock and roll. But you can't get rocks unless you've got silicon and aluminium. You can't get rabbits unless you've got carbon, oxygen, phosphorus, iron, what have you. And you certainly don't get any rock and roll. So how does it get these things to stick together, these protons? Because remember, protons don't like each other. They, as far as the electromagnetic charge is a real turn-off. And to try and get them as close as they are in the nucleus, we're talking about an immense force. But what we'll see is that, right, from the discovery by Rutherford et al., for the first 50 years or so, it becomes clear, due to the work of a number of people, but probably most importantly Hans Bethe, that you could easily make a 2-proton nuclei. We could get some helium nucleus. We'd still have mostly protons, still have mostly single protons, mostly hydrogen, but we would also could make some of this helium. So we understood how to get them too. But it seemed virtually impossible to get beyond that. To build any decent number of nuclei with more than 2 protons. And we know that's vital. You know, if we're to get anything interesting, you've got to be able to do that. And it's this astute guess that I will be hoping to explain that good old Fred finally came up with. Now, so let's start with how we build up right from the beginning. Where are you? Right. When we're building the nuclei, now let's see, yes, yeah, right. When we're building the nuclei, when we're building molecules, all the chemistry that I've talked about that is vital to do this, all of that, really one interaction dominates all of that. That's the electromagnetic interaction. And it's between the electrons floating around the thing. But in building nuclei, two more interactions come into play. What was called in those, well, for much of the 20th century, it was called the strong interaction, which was strongly attractive between nuclear particles, but very, very short range. And also a thing we call the weak interaction, which we'll see as a somewhat weird force that can change one elementary particle into another, but that has an absolutely minuscule range. When I was first researching in Edinburgh physics department, we had guys like Nick Kemmer, he was Peter Higgs's boss. He was seriously contemplating that Fermi's model wasn't good enough and that the weak force might actually be a contact force, that you had to get two, it was so short range, you had to get two things into contact. The properties of these, right, the strong is acting between neutrons and protons. We'll come to neutrons in a minute. Neutrons look just like protons, except they don't have any electric charge. In fact, Heisenberg thought they were the same. They were just two different states of the same particle. That's not quite what we think now. The strong force was very attractive over this tiny short range, a femtometer, 10 to the minus 15 meters. I'll keep calling it a femtometer. Nuclear people tend to call it a Fermi, after the great Italian nuclear physicist, and it trips off the tongue better than femtometer. But to emphasize when we're talking about a distance, I'll stick with femtometers. If you try and push neutrons and protons together to closer than 0.8, then the thing becomes repulsive. But it's strongly attractive in this region here. The weak only seems to happen inside these nucleons, what I'm going to call the neutron and the proton, which call them nucleons. And it can change a neutron into a proton. If you've got a neutron just floating around in your lab, within 10 minutes or so, it'll turn into a proton. If you have a proton and you bang it hard enough, give it enough energy, then it will turn into a neutron under the weak interaction. But these are very, very slow interactions when you're dealing with the proton, and as I said, of infinitesimal range. But we need both of them to build the nuclei that we have. And to get a better understanding, we'll need to peer behind this femtometer veil, which I hope to get to later. Right, so what happens? We have the Big Bang. Up to 1 second, forget about it. It's chaos. From 1 second, we'll have a stability of sorts. It's called the neutron-proton freeze-out. And we, from that time onwards, for the next 20 minutes, we'll get fusion. We'll have protons, which themselves on their own form a hydrogen nucleus, and we'll have neutrons. The neutrons obviously on their own can't attract any electrons, they got no charge, so they can't make atoms on their own. And at the end of this second, if we go back to say at a 1/10 of a second, we've got an equal number of neutrons and protons, but by the time we get to a second and this freeze out, we've got about 6 times as many protons as neutrons. And we will have, during that first 10 seconds, we'll have some fusions, but they'll quickly get broken up again. The universe at this sort of time is dominated by gamma rays, and gamma rays will bash stuff up like nobody's business. So we have to wait until about 10 seconds where this number will stay the same roughly. We'll be having fleeting formations of deuterium, tritium, helium, but they'll all break up again. But from about 10 seconds onwards, we'll start to get a relatively permanent fusion of protons and neutrons. The main ones are the collision of these two. The neutron can get close to the proton, and when it does, if it gets within the 2 femtometers or so, it'll fuse together, and we get another nucleus, which is still going to be a hydrogen nucleus. So what the notation here, the letter will be the element name. So you need to know your chemistry to know that's hydrogen. And the letter up here, the number up here tells you how many nucleons are in it. I could also put a number down here that would tell you what the atomic number was, how many protons were just in it. But as long as you know that's hydrogen, then you know those two are sufficient. This is such an important little nucleus, twice as heavy as a normal hydrogen nucleus, that it gets its own name, the deuteron, D. Once we've got a deuteron, it will bang into some more protons, and another neutron will join onto it, and we get this with 2 protons and 1 neutron, which is a helium nucleus because it's now got a charge of 2. It's not the one that's the majority of your helium in your helium balloon. That is helium-4, which has 2 neutrons. This one only has 1 neutron, but it turns out that's enough to stabilize it. So there's a fraction of helium-3 hanging around now that was made then. We can then get a deuteron banging into a helium-3, and this forms this wonderful thing here, which is our helium-4 nucleus, which is very tightly bound. The 2 protons line up nicely together. The 2 neutrons line up nicely together. The neutrons serve to keep the protons together. And this thing is so ubiquitous in nuclear physics. You'll often find me calling it an alpha particle, because when you have these huge nuclei of uranium and polonium and what have you, radium, they're often breaking up, and they shoot out a little helium nucleus to ease stresses in those big nuclei. And we first saw them, didn't know what they were. We saw 3 lots of radiation coming off, and we called them alpha, beta, and gamma. Turned out the gamma were the photons, the beta were just electrons, and the alphas were these little beauties here. So they're an alpha and a P. And these are all stable. So we still have them around. You get other things happening. We get a deuteron banging into a neutron. Neutron will join up with that. So we have 2 neutrons. So we have an even heavier form of hydrogen, which we call tritium, because it's got 3 nucleons in it. You might think that should be stable, but it isn't. It lasts for a while. It's got a half-life of about 12 and a bit years. During these first 20 minutes, that can also give us a route to helium, in that we get a deuteron banging into another one of these, and we get this reaction here that we've got. The deuteron is the proton and the neutron. The tritium is the proton and 2 neutrons. It ends up with 2 protons, 2 neutrons, our wonderful alpha particle, plus a spare neutron. I mentioned that one. It's not so important, but I mention it because it's the one that's the favored reaction for fusion power here on Earth. If we can get, this is the sort of thing that you're looking at Culham Jet and at ITER in France. What we don't get, and this often surprises students, we don't get 2 neutrons sticking together. And, you think, well, if the neutron, the strong force sticks the proton and the neutron together, why doesn't it stick 2 neutrons together? And there we don't have to worry about electrical repulsion. We don't get it, and we don't get it through, we have to do a bit of quantum mechanics to show why we don't get it. But basically it comes down to the exclusion principle. Because the neutrons are identical particles, they can't occupy the same state. So they can't actually both get in the lowest energy state of the, that they would want to. They can't get close enough to each other. Therefore they don't get within the full range of the strong force. The same thing stops us getting, this is the most common collision in those first 20 minutes, is two protons banging together. And, you know, that's the most common collision in the sun as well, two protons banging together. But we don't get them forming a helium-2 nucleus. Exactly the same things apply there, but we've also got the fact that there's this ginormous electrostatic repulsion, which is sort of 10 billion times stronger than the repulsion you'd get if you tried to bring two molecules close together. You know, if we compress something and the electrons start objecting because they don't want to be too near these other electrons, the forces here are enormous. Then we get to 20 minutes and it's too cool for any more of the fusion. So after the first 20 minutes, in the first day, any free neutrons left that haven't been taken up in fusion, they will decay to a proton via the weak interaction. You know, I said that half of them go in every 10 minutes. By the end of the first day, there won't be any neutrons left, any free neutrons. End of the first century, there won't be any free tritium left. It'll have all gone to helium-3 via a weak interaction. And the basic upshot for the next 100 million years is that we've got just two nuclei. Therefore, we've got two chemicals, two gases. We've got hydrogen and we've got helium. That's the number percentage. Because this is 4 times as heavy as that, then the weight percentage is much bigger. You've got about 26% in weight, but in terms of numbers, that's what you would come across. We get small amounts of D and He left, but it's less than this amount. And there is a very tiny trace, about 1 nuclei in about 10 billion will be a bigger one of lithium. But it doesn't help, it turns out. So what's that? That's basically a boring universe. You're not going to get any evolution there. Forget it. So what happens over the next 100 million years? Well, good old gravity comes in and creates fusion all over again. And it does so by gradually clumping the stars until they get hot enough and dense enough in their cores to give a vast number of these collisions. And these collisions, those are the two things we've got. We've got protons, we've got helium-4 alpha particles, so they bang into each other. But it turns out it's not that hopeful. In the Big Bang, if you remember, we needed the neutrons. We kicked it all off by having neutrons banging into protons and forming deuterium. But we don't have any free neutrons now. And when the protons bang into the helium-4, they don't produce anything stable. It breaks up again enormously quickly. So the only hope is that the energy of a proton collision will allow a weak interaction to turn one of the protons into a neutron before they separate again. And then we could get a deuterium. Now we know there's fusion going on in the sun. So we know that must, in all the stars, something like this must be happening. And it was Hans Bethe who worked out that what must happen is when two protons come close enough together, if just at that time the weak interaction turns one of them into a neutron, then you've got deuterium. So you get this reaction. You get your D, and because when the weak turns the proton into a neutron, there's still got to be a conservation of electric charge, and that's a positron shoots off, and there's also a neutrino shoots off, and you get this amount of energy given off. Now, you know, the chance of that happening is bloody tiny. And if you took a proton, a particular proton in the core of our sun, and you said, right, how long is it going to take before it gets to be involved in a collision where a deuteron will be formed? The answer is 9 billion years. So most of them don't get to do it. The sun's only is less than 5 billion years old. So most of those protons banging around have not yet managed to get fused into a deuteron. But because such a gigantic bloody number of them, they're happening all the time. And so, vast numbers of deuterium nuclei are being made every second in our sun. And then we get the deuterium will bang into another proton. And that's now, we're back to what happened in the first 20 minutes. Fine, that happens easily. It takes the average deuteron only 4 seconds to turn into helium, compared to 9 billion years for 2 protons to get you a deuteron. Then if 2 of these helium-3 meet, then they will make helium-4 with a couple of protons left over and a big amount of energy. Now that takes about 400 years, largely because there's not that many of these helium-3. They've got to wander around until they meet a mate. And when they do eventually meet a mate, most of the time they're just meeting more bloody protons. But when they meet another helium-3, then bang, you've got this. And what have we done? We've made some more helium-4 alpha particles. Now this was worked out by Hans Bethe. It's called the proton-proton cycle. And it all looks like that. So you start off with 4 protons up here. The red things are the protons. The little nu is a neutron, and the white thing is an electron, a positron, sorry. When you see that, you know that's had to have a weak interaction. The neutrino here, that's all that ever affects a neutrino is the weak interaction. The strong interaction, the color interaction, electromagnetic interaction, it ignores all them. It only ever takes part in a weak interaction. So anytime you see a neutrino coming off, you know that to be a weak interaction. But once those 2 weak interactions have gone, we now got a deuteron. It'll bang into another proton. It'll produce a helium-3. When that happens twice, they come together, bang, bang, and there we are. There's our nice alpha particle. Now, I've gone into detail there because that is what gives us most of the energy we're getting at the moment. The vast majority of the energy from the sun is that. But it gets us nowhere in terms of making carbon and iron and all those interesting stuff. So what happens? Right, well, imagine these first stars. In these first stars, that's the only thing going on. In these first, it's population 3 stars, I think, aren't they? They're called. We get the populations the wrong way around. So population 3 are the first. And we know that what will happen is towards the end of its life, but when it's burning, these things are big. They're bigger than us. They were bigger. Those population 3 stars were certainly a lot bigger than our sun, largely because they were only dealing with light nuclei and the general environment was a lot warmer than it is now. So you tended to need, you think of sort of like a gas law thing, you tended to need more of them and bigger to produce the fusion at the core. And once you got a big star producing fusion at the core, it doesn't last as long. So these things, they lasted, a typical one might be 5–10 million years, as opposed to the many billions of years of our sun. But during that time, they're burning away the hydrogen and forming the helium. And gravity will make that's 4 times as heavy as a proton. So it's going to sink to the center. So what you're going to get in the central core is a buildup of helium. In that core, we'll get a vast number of protons still banging in, and we'll get a large number of these. So people thought, right, well, can't we then just build up from there? But it turns out that when you bang a proton into an alpha particle, it breaks up virtually immediately. we get a thing called lithium-5. It lasts about the length of time that a photon would take to travel across it. It just doesn't last and just breaks up again. Well, it's a bit long, yeah. Alpha also breaks up, but not quite so quickly. They will come together and form very briefly this thing here with 4 protons, 4 neutrons. 4 protons means it's beryllium. We've, you know, our periodic table goes hydrogen, helium, lithium, beryllium. So, but the trouble is the beryllium breaks up back into the helium. It forms a resonance. Willie Fowler showed in the 40s that there was a nice resonance with the 2 colliding alpha particles, which meant it could last a lot longer than that. But a lot longer than that is 10 to the minus 16 seconds, right? Which is still not very long, and not much can happen. That is hardly a stable platform upon which you can build other stuff. Too short for it to fuse with something else before breaking up. So that was the puzzle, and it was called, by the time we get to the 50s, it is the beryllium barrier problem. How do you get beyond bloody beryllium? There were extreme events, right, where all sorts of weird things can happen. Breakup of neutron stars, supernova explosion, huge energetic cosmic rays coming in, breaking stuff up. And some of that would leap fusions of things, but didn't seem like that could be anything like enough to give us all the stuff to make all the rocky planets and ourselves. And Fred, who had been thinking about this since the end of the war, in around 1952, says, look, I'm here, we're all here. There's got to be a way of making it. And he knew enough. Remember, Fred he described himself as a theoretical astronomer. We'd call him a cosmologist probably now most of the time, but he did a lot of astrophysics. And he said that there's got to be a way of doing it. Bang, bang, bang. And he said it would all be possible to get all these, if only the stars could make this nucleus, the carbon-12 nucleus, a very, very tight, stable nucleus that would be there and would support all sorts of chains of fusion reactions and make all these other stuff. So how could he get from beryllium to there? This was his guess. He said, suppose during that 10 to the minus 16 seconds, a third alpha particle collides head on with the beryllium. You've now got 3 alpha particles, which is 6 protons, 6 neutrons, which is exactly what you have in carbon-12. And he said, suppose there was a state of the carbon-12 nucleus that was very close in energy to these 3, this beryllium-8 and the alpha particle that gets up close. Now that was very energetic. He worked out it would have to lie at least 7.5 MeV, a long way above this carbon ground state. So I'm going to call it carbon-12 asterisk. It's called the Hoyle state, but I don't know what the general symbol is. But usually when you see an asterisk, it means an excited state of something. So fine, he said, if there's an excited state there that's compatible enough with this configuration of a brief beryllium, 2 alphas stuck together and a third alpha banging into them, then it might fuse over into this. And then if that could decay, drop down, lose all that excess energy before breaking up to form the carbon-12 ground state, then you would have something you could work with. The stars could work with to build more stuff. Now that decay, everybody admitted that decay was unlikely, but certainly not impossible. And if we get that forming, then the chances are we would get some of this and the star would have a stable carbon nucleus. Of called the triple alpha process, because 3 alphas are involved. First of all, they collide. Now that negative sign of the energy there means this thing is slightly higher in energy than these two. So you've got to add stuff in there. Then when another helium comes in, bangs in, we get this massive excess of energy. And the thing would look a bit like this. 2 alphas come in, they form this brief beryllium thing there. There's the 2 alphas. And then they form, the 3rd alpha comes in, that joins to there, causes the Hoyle state, which then gets rid of, and it has to take 2 photons to get rid of it, and produces this tight carbon-12. Fine, great. You know, everybody said, right, why didn't we think of that? And then they suddenly realized why they didn't think of that. It needs very high temperatures. Well, they would exist in those type, the cores of these aging type things. You're looking at a star that is going to be like Betelgeuse, right? It's going to have a coolish remains of hydrogen outer, big red hydrogen outer, but an enormously dense helium core. And you remember, this is helium, right? Light as you come. At the core, you need to get it about 10,000 times the density of lead in that core. So it would only be possible when the star was getting very much towards the end and gravity had had a chance to concentrate that. But he goes along and he talks to people like Willie Fowler, who had done all the work on beryllium. He goes to the lab at Cornell, and they initially dismissed this completely out of hand. The shell model that was then just coming into vogue as the current best model didn't produce anything that would look like the Hoyle state, this excited state. This excited state's got to look like a cluster, pretty much like a cluster of an alpha and 2 alphas close together and another alpha stuck in. And they didn't, the shell model didn't support clusters like that. It was just incompatible. They weren't sure that it would relax to this. Most of the time it'll just break up again anyway, even if it did. But they just did not believe in the existence of that state. But there was a guy, there was a bit of apparatus, of Van de Graaff apparatus doing nothing, and a guy had just joined Cornell, and Willie Fowler says, well, you can go and look for it. And he found some evidence of something funny happening around that energy. But then a few years later, there was more experimental evidence found around about 57 that looked like Fred Hoyle was right. That it's taken now nearly 70 years for us to actually be able to do the calculations that say, yeah, there is a state of carbon that looks just like the Hoyle state. Even those calculations are still very much first order approximation level. These are very difficult calculations to do. It doesn't look quite like that, that diagram, which had the 3 alphas forming a sort of triangle. It looks much more like a bent arm. And it's much bigger than the carbon-12 ground state. It's about 40% wider. But it's there. It does look like it's there. So after 70 years, we can say, yeah, Fred, what you were suggesting was right. We now know that every 2,421 times, when it breaks up again, it goes to the ground state of carbon, and we get carbon. So we now believe that's how you get around the beryllium barrier. It's it kicked off really the talk of the anthropic principle. People saw this coincidence of this excited state of carbon with the triple alpha collision as something so weird that it suggested that the universe was designed in some way around producing us, or else we exist only in universes that can do this. You know, the anthropic principle, we could talk about, have a whole goddamn evening talking about the weak and the strong, or the variants of this. But that's really what kicks it off, I think. Once you've got carbon-12, it's all easily done. I'll not bother going through them long. There's a thing called the alpha ladder, which very quickly gets you oxygen-16. Oxygen-16, the standard, very, very stable nucleus, a doubly magic number nucleus, so that it's very difficult to get oxygen to break up. That quickly forms once you've got the carbon-12. In fact, people then use that as another argument for anthropicness, because if it was just a bit quicker, it would mop up all the carbon-12. And without any carbon-12, you don't get any life. But it seems to be just that there is a resonance between carbon-12 plus an alpha and this that is just far enough apart to slow this up a bit so it doesn't absorb all the carbon-12. But actually, we get a hell of a lot of it, as I think you'll see. So there we are. That's a similar sort of energy. And once you've got oxygen-12, you quickly build up, adding an alpha particle each time, and you get all the way up to iron. There's other processes, but this is the one that has made most of the stuff. And if we look at elemental abundances in the solar system, when we add an alpha particle, we're adding 2 protons, so we're getting even number nuclei. Here's the atomic number. This is telling you how many protons are in. And you'll see that all the even number nuclei, we have a lot more. This is a logarithmic, log 10 abundance. So for example, the difference between oxygen, you see how oxygen's more than carbon. Carbon kicks it off, but oxygen actually grabs more of it. And the worry was that, right, if the higher up that goes, the lower down this goes. But if you look at the difference there, we've normalized it to I think, what is it normalized to? That can't remember now. Is it iron 56? No. Anyway, whatever we're normalized to there looks like beryllium, doesn't it? We've got 10 millions worth of, well, no more than 10 millions worth of oxygen, more like 50 million worth of oxygen compared to just 3,000 of fluorine, which is an odd number, and then back up for neon. And so these are all what are called the alpha chain nuclei, and it stops when you get to here. And then there's a quick drop to these much, much heavier ones lower down. And although, remember, again, it's roughly speaking, we've got 1,000 of all these light ones for every one of these heavy ones. And that's because we can't get beyond iron and nickel with the alpha chain. If we look at the actual energy, how deeply bound these things are, and you imagine something trolling along the top here free, when it's bound, it drops down and releases all this energy. And right down at the bottom, we got iron 56. If we're now trying to add stuff to these, we're having to add energy all the time, every time we come up here. So these would be cooling reactions. We have to think of a different way of getting them. Usually we see most of them being made by just capturing free neutrons. I said we don't have free neutrons. That was a problem at the start. We don't have free neutrons. Well, we occasionally get free neutrons. We get them in things like when neutron stars merge, we get a blast of free neutrons. When we have a supernova, when it will implode and then explode, there will be a blast of free neutrons. And during that time, your heavier elements like iron and stuff can capture some of these, and they build up. And we have a process called the R process, rapid series of neutron captures. Now, capturing a bunch of neutrons doesn't get you to a new element. Remember, you have to get a proton. So what you have to have, because above iron we're needing more neutrons than protons to keep it stuck together, you have to have a lot of them happening. So this has to happen during a big storm of neutrons. Later generations, once you've got stars that have been had the logistics of the alpha chain, the star comes to the end of its life. If it's a big enough star, it'll blow up, it'll shed the stuff. So when we look at our stars, we have lots of alpha chain nuclei in there. And when you get into population 2, you will have our process nuclei as well. And then you can also get a slower process happening within the star, signal neutron captures. So this stuff is all well understood. How we get all the rest of those is well understood. The main point I want to emphasize is that carbon-12 is a good seed for the S process. When these R process heavy nuclei decay and produce some neutrons, then they bombard that and we build up again some of the others. So it is all well understood, and none of that is particularly contentious, whereas the Hoyle state was very contentious and is still seen as an argument for the anthropic principle. Once you've got carbon in your star, and there's a funny thing about astrophysicists, any star that's got more than hydrogen and helium in it is said to have a certain amount of metals. Now, carbon isn't a metal, nitrogen isn't a metal, and oxygen isn't a metal. But many of the bigger stars, this cycle, in modern stars, this carbon-12 acts as a catalyst for creating more good old alpha particles. But this couldn't have happened in those early stars because there wasn't any carbon-12 to act as a seed. But in stars bigger than our sun, it becomes the dominant process. It's called the CNO cycle. Hans Bethe also worked on that. There's a whole little chain goes through. There's two weak interactions, one there's a neutrino, there's a neutrino, but they're happening just within a nucleus. And weak interactions within a nucleus, it's got a long time, it's jiggling about, there's all sorts of energy going on in there. So sooner or later you get this decay into things, and it does that and that. We don't need to bother with the details. But we get carbon back at the end. So carbon acts as a sort of catalyst for producing yet more methane, yet more helium, and that's what we've got. About 2 or 3% of our energy comes from this because our sun has a certain degree of metallicity, and it uses carbon that way. But if we look at some of the bigger neighbors that we've got, most of their energy is coming from that rather than from the proton-proton cycle. So that's what it looks like, but we don't need to go through all the details, but bang, 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 that's running around. Leave it at that. Now, have we time? That's an hour now. Do you wish me to go? It would take about another 20 minutes or so to lift the veil of the femtometer thing, to look at what's causing the protons, what's causing the neutrons, and why we're never going to see these things called quarks. Why we're never going to see them free. I don't know. Has everybody had enough?
I'd say go for it, John. You only live once.
Right. Yeah. I'll send Michael all the slides and a write-up, so you'll be able to do that at your own thing. But I'm sure you've all heard of quarks. They come in two types. There's the up type, which is these three, up, charm, and top. They're all called the up type because they all have charge of 2/3. The down type have a charge of -1/3, and we've got down, strange, and bottom. The U and the D are the lightest ones. These are the ones that concern us in our nuclei. These things here, they're much heavier and they're more energetic. And you can see how, if you look at the mass in terms of GeV, if we look at the top quark, 171 GeV compared to 2.4 MeV for an up quark, that is an enormous difference. You know, it is sort of a couple of 100 times heavier than a nucleon, and it's just a quark. But anyway, there's those three. They have fractional electric charges, and there are those three generations. And at stellar energies, we just need to worry about U and D. And when we talk about charge in modern quantum theory, charge is the ability to emit and absorb carrier particles of the field, carrier excitations of the field. The electric charge is the ability to emit and absorb photons. The photons have no charge and they have no mass. And it's the exchange of photons, in particular virtual photons. You don't need to worry about that. It's all quantum field theory. Let's not get into that. But they are what cause the electromagnetic interaction. What we have in quarks is a new type of charge that we didn't know about called color. And color charge comes in three different forms, which naturally enough, we call it red, green, and blue. And color charge is the ability to emit and absorb gluons. And it's the gluons that we now see as creating the strong interaction. The gluons themselves, like the photons, they have no mass. Most field particles prefer to be bosons with no mass. But the vast difference, which leads to an enormous complication, is they are charged. They carry color charges. They carry a standard color charge and an anti-color charge. If we think of in the electromagnetic interaction, we can think of as plus and minus as just the anti-charges of each other. You know, the electron has a negative charge, its antiparticle, the positron, has a positive charge. Here we can have a red charge, a gluon with a red charge and an anti-green, and weird things like that. Because the gluon has charge, that means the gluon can itself emit gluons and interact with other and absorb gluons and interact with them. And it makes it a hell of a lot more complex than the electromagnetic interaction. It's also a lot stronger. By stronger, I mean the ability of the charge to emit gluons. Color charge emits gluons much more readily than electric charge emits photons. The nucleons, protons, neutrons, they contain three, one of each color. And because we're calling them red, green, and blue, the choice of that was because you think of red, green, and blue as producing white, and white is sort of colorless. And it turns out that to get beyond the femtometer veil, you've got to be colorless. So you've got to have no net color in the thing. A proton's got two U quarks and one D quark. So we've got an electric charge of 2/3 plus 2/3 plus minus 1/3, which equals +1. The neutron has two D quarks and one U quark, which gives us minus 1/3 plus 2/3, which again is 0. So apart from the fact that one of the D's has become a U, that's the only difference between these two particles. But then it turns out the neutron, the D, is a heavier quark than the U. The neutron is a higher energy state than the proton, which is why when it's free, the neutron will decay into a proton. But it's not the strong charge that does that. So each quark in a nucleon has a different color, right? So they're colorless. The nucleons have bulk and the quarks don't. The quarks, like the electrons, we assume in all our modern physics, we assume that what we've got is point particles. Elementary particles are point particles. Let's not get into strings. If we get down, drop you know, many orders of magnitude. Let me just put a light on here. If we drop many orders of magnitude and get down to the putative strings, which I am far from convinced about, then we do have a finite size. But as far as we're concerned here, they're point particles. Quantum field theory assumes they're point particles. No finite size, whereas nucleons are this big, 0.8 to 1.5 femtometers. And, you know, nuclei have finite sizes. That's why, you know, when we get to these really big nucleuses, we need more neutrons than protons, because the protons are getting too far away from each other. If you take a uranium nucleus, a proton on one side of it is too far from a proton on the other side of it for the strong force to work. Whereas the electrostatic repulsion is still bloody enormous. So we've got this, the fact that we can't compress it to more than 0.8 says that they're all, you know, they all get bigger. The nuclei, a big nucleus is physically bigger than, it's a bigger range really than atoms, not than molecules, but than atoms. Atoms tend to just tighten in. We call them hadrons. You know, this awful propensity of using Greek and Latin and sometimes mixes of the two. Hadros is Greek for bulky, so we call them bulky. And you will see a representation of them looking like that. A gluon is always drawn as a little spiral, a little helix. And there's our red, green, and blue, UUD, blah, blah, blah. In fact, it's not really like that at all. But let's look at what the gluons can do. If we've got a quark with a red, an up quark with a red charge, it can emit a gluon. It can emit all sorts of gluon, but it can emit one with a red charge and say an anti-green. Now, so in that emission process, we see that we've still got conservation of color. We've got a green and an anti-green. We leave the U quark now with a green charge, and the gluon carries away the anti-green. Those two cancel each other, and we're left with just a red. If that gluon now hits a D quark and is absorbed, and the D quark has a green charge, then that green charge will be cancelled by the anti-green in the gluon, but the red charge will be absorbed, and the quark has now got a red charge. So the net effect is the two quarks have swapped colors. We've started off with an up quark with red and a down quark with green, and we end up with an up quark with green and a down quark with red. And that's the interaction that's going on. That's the basic interaction that's going on. And that's creating the really strong force between quarks. But, you know, as I said, the gluons themselves have got charge, so they can do all this stuff. They can emit other gluons. And we end up with what it's really like. This is a sketch of, and even that is, you know, it's a simplified sketch. Here, we've abandoned the color convention in that green here now represents a green ball is a quark, and an orange ball is an anti-quark, and those are the gluons. And you see there are places here where a gluon is coming along and emitting other gluons. A gluon can fly through the end, create a quark-anti-quark pair in the way a gamma ray can create an electron-positron pair. It's virtual, it'll disappear after a time. We get the quark again going in there. So we end up with this sea of quark-anti-quark pairs and gluons, as well as just three, what we call now valence quarks. You see there's a green one there that's unpaired with anything, a green one up there and a green one over there. So those would be the three of the previous simple diagram. But inside we've got this. And this is a glimpse of well below that first second. If we looked at the universe in the first millisecond, we'd see a quark gluon plasma with a lot of electrons and neutrinos as well, but it would look a bit like that. Now, why can't we? The color confines the quarks behind this femtometer veil. Why is that? Why does it do that? What happens is the gluons, if we got two gluons, two photons can go by each other. They don't notice, you know, they don't interact with each other. It's the great thing about photons. They tend to ignore each other. Two light beams will pass through light beams without scattering off each other. That's not the same. Gluons attract each other. So instead of spreading out, a photon field will spread out beautifully uniformly. The gluon field will start to spread out uniformly, but very quickly, the charges on the gluons will attract each other by exchanging other gluons, and they end up forming tubes. Flux tubes are always, technically, I think they're called Lunt strings. If you think of these as like elastic bands, and if we try to move two quarks apart, we'll get this gluon tube between them, and the energy is roughly 1 GeV. That's like 10 protons worth of energy per femtometer that we try and pull. If we try and pull them 2 femtometers apart, it's take 2 GeV. So you see, to try and pull them completely out of this femtometer veil, it's a ludicrous amount of energy. Now, in fact, what happens is once the energy gets of that order, it's much simpler to create a quark-antiquark pair. It doesn't take anything like that much energy to create a quark-antiquark pair. And so that's what will happen. Suddenly this tube will snap and leave the two quarks no further apart, but we get a quark-antiquark pair, which is free to move away. As long as the color on the quark is the anti-color, the color on the antiquark is the anti-color of the color on the quark. So that forms a colorless pair. Right, so suppose we have a collision, we say, right, let's bang in. We go to the Large Hadron Collider, we bang in one proton against another, which is what's happening in the LHC. Remember, if you could see them, it would look like two pizzas, because the relativistic foreshortening would be such that instead of these two spherical-looking protons coming at each other, it looked like two pizzas banging at each other. But let's look at what happens. Suppose one has come in, it's gone away again, but it's knocked this U to try and move it out this way. So the U and the D want to go that way, and the U goes that way. And we get this gluon flux tube between the two. And when it gets long enough, we'll form a quark-antiquark pair. This quark-antiquark pair, that one, I've chosen a down quark, or well, not me, whoever drew this, will spring over to there and produce this pairing of a quark and an antiquark, which in this particular case is what we call a pi meson. And it's a pi meson with a plus charge. The anti-down has a plus 1/3, the up has a plus 2/3, so this has a plus 1/3 charge. So this colorless hadron, which we call a meson, goes floating off, and that one goes back to there, and we've now got a neutron. So in this collision, we've banged into the proton, created a neutron and a meson, but we've not managed to see a free quark. And what we end up in these big LHC collisions is that with huge energies, this thing is happening, a great string of these happen. And we have a string, well, they call it a jet. So we get jets of hadrons flying in the direction that the initial quark tried to get away in, but we get no quarks. But you'll hear of these jets, which are, and the jet in fact can contain nucleons as well. You can get it so that when you make enough of these pairs, some of them will join up and we'll get 3. So we get a sort of hadron jet generally. But the easiest ones to produce are mesons, and the most common are this one, which is the one of the previous diagram, which is an up quark and an anti-down. So that's just saying what I've said, a whole jet of hadrons. The femtometer veil hides the quarks from us, and we call this process hadronization. where we try and pull the quark out or bang the quark out with as much energy as we can muster, all we get is a bunch of hadrons. We don't see a free quark because the gluon flux tubes will break down into mesons and ultimately into baryons as well. Baryons are things like the proton and the neutron, bary for heavy. Mesons were, just have the two. Mesons were invented by Yukawa, who guessed that what he called the strong force, the attraction between a proton and a neutron, between the nucleons, he guessed that it was done by an intermediately massive particle he called the meson, of middle mass. Now, we now know that the strong interaction is not the exchange of mesons. That's only what's happening on the outer bit of it. The strong interaction is color charge and gluons between quarks. But the range of that isn't big enough to act between nucleons. You know, it will, long before we get to between a neutron and a proton, we'll have had our flux tubes collapse into this meson shower or meson jet. So what we now call this interaction between the nucleons, we now call it the residual strong interaction, because it's the stuff that happens at the end of the range. And the two mesons mainly involved are the up and the anti-down, and the anti-up and the down. That's got a negative charge. They're both called pi mesons or pions, pi plus, pi minus. There's also a pi zero, which would be U and an anti-U and a D and an anti-D, but because they're antiparticles of each other, they don't last very long. They're so close together, they'll quickly annihilate. So the pi zero state, which is actually a combination of the U anti-U and the D anti-D, it doesn't play the great role. These things are about as big as, about as big as a nucleon, but only about a seventh of the mass. There are much heavier ones, and we've been finding, you know, there's a great interest in mesons made with the bottom quark, which are very, very heavy mesons, which are causing us some interest in probing the standard model at the moment. We can get excitations of these. And we can work it all out with the quantum mechanics of the stuff. We can guess what they are. But the pions are colorless, so they can come out and they can wander along, and yet it still don't get much more than 2 femtometers. You know, the furthest you're likely to get one is maybe 10 femtometers, and that's largely down to this problem. That when we do the force field due to quantum mechanics, due to the exchange of these particles, there is this additional factor, this exponential decay factor that depends upon the mass. Now, for the gluon field, that doesn't limit the gluon field at all because the mass is 0 and e to the minus 0r is 1. So we just get the 1 upon r squared. But with the gluons, they're limited by their charge attractions. They're too attractive to each other. With a photon, though, photon has no charge and no mass. So all we get is the 1 upon r squared fall off that we're all familiar with. Same as with if we ever have a graviton theory of gravity, we'll get the 1 upon r squared fall off of Newton's law. We'll see why that comes about, because the graviton is no mass and very little charge. But pions are 300 times heavier than electrons. So they're dominated by this factor, not the spreading loss, but by this factor. And that factor means the ability to exchange a meson between two protons or 2 neutrons, or a neutron and a proton, that ability to exchange it gets to near 0 after a few femtometers. Boom. Right, yeah, I've done that. There's the weak interaction. The weak interaction is the last thing we have to do. It has field carriers which don't have exotic names. They're just the W and the Z. There's a W plus, a W minus, and a Z, which is uncharged. These are enormously heavy. The Z boson you can think of as being like a photon, only with an enormous amount of mass. They're 100 times heavier than the whole of a nucleon. And you think, well, how the hell can that happen inside a nucleon? How can a neutron have, for a neutron to change into a proton, it's got to emit one of these W plus bosons. W minus bosons. But that's the wonder of quantum field theory. It can do it, but only do it for a very, very tiny time. And that limits the range of the thing to about 1,000th that of the strong force. I mean, the real strong force, not the residual. Let's just see how they change it. If a D quark emits a W minus, then it becomes a U quark. The total electric charge is the same because the U quark, that has minus 1/3. The U quark has plus 2/3. And the W boson, the W minus boson, has -1 charge. So that adds up to minus 1/3 on both sides. Similarly, if a U quark emits a plus, W plus, then it turns into a D quark, and we have the same thing again. But it's so far off the mass energy conservation shell that it's only the W can only last this tiny little time, and it decays. W minus decays into an electron and antineutrino, the W plus, the positron, and the neutrino. We saw those decays when in the proton-proton thing and in the CNO cycle. The free neutron decay now, which is that, we can now see that what's happening at the quark level is that one of the Ds is changing into a U. We emit the W minus, so we get this. The W minus decays into the electron and the antineutrino. And in neutron-rich nuclei, such as in the tritium, when the tritium's decaying in those first few years after the Big Bang, then what's happening is that we're getting the neutron turning into a proton. And again, we get a W minus and an antineutrino. There's the proton weak reactions. So that, what's kicking us off is that. I should point out that still some of this is speculation. When we look at the calculations, and this is the last slide, I promise you. The standard model. The standard model assumes, and I covered this, most of you want to see this probably, but when we discovered the Higgs, I did a series of 3 articles trying to describe what lay behind all the standard model and the Higgs mechanism. Or maybe send the late copy of that to Michael. But we have the standard model assumes 3 exact symmetries, one of which is called U1, which leads to the electromagnetic interaction, and one of which is SU3, which is what gives us the color interaction, what we call quantum chromodynamics. As quantum electrodynamics is the fancy name for quantum field theory of electromagnetism. Quantum chromodynamics, the field theory name for the color interaction. Those are exact symmetries. And the standard model tells us the rules that those exact symmetries give. It gives us both lots of rules. When we apply those rules to QED, the accuracy, the precision we can get is absolutely phenomenal. And yet in quantum chromodynamics, it's crude. What we can do is crude. We cannot yet theoretically derive that hadronization process. We've got various little approximations that tell us that's what's happening. We've got experimental support for what's happening, but an ab initio calculation of what happens when we move one quark, say, a femtometer away from another, it's beyond us. It's beyond us partly because of the complexity of SU3 compared to U1, which includes the fact SU3 tells us that the gluons will be charged, but also the strength that we normally work in a perturbation series where you think of an initial interaction and then a second order interaction, which in quantum electrodynamics is less than 1% of the contribution of the initial one. And the third order is less than 1% of the second order, and so on. So it all quickly converges, and we can do wonderful calculations. But that doesn't work with the strong interaction. The coupling constant is virtually 1. So no matter how complex the situation in that funny diagram, it contributes just as much all the time. So if we compare the two there. So yeah, we can't calculate the hadronization process. So we have all sorts of simplifications. And you may hear of these, if you read some of these, you'll hear of a thing called isospin, which is an SU2 symmetry, but it's not exact. And you'll hear of flavor symmetry, which is SU3. And SU3, the maths is identical to the gauge theory symmetry that underlies the standard model. But this is an approximate symmetry that was the thing that led Zweig and Gell-Mann to predict the 3 quarks. And it worked, assuming the up, the down, and the strange quark were all of the same mass. They were all symmetrical. Everything would be the same if you swapped a U for a D and a D for an S and an S for a U. We know that's nothing like true. And the isospin symmetry assumes that everything's the same if you swap U and D. We know that's not true, but it's a lot truer than this one. So, and once we assume these SU2 and SU3 symmetry, theoreticians like me get happy because we can play around with, we can construct ladder operators, we can see what particles we should be able to construct, what baryons, what hyperons, what mesons we should be able to construct. We can see why 2 neutrons won't stick together, things like that. And it helps us with stuff like that. But once you start seeing actual detailed wave functions, like if you look in Wikipedia, you'll see a nice expression of 9 superpositions for the proton wave function. It's not exact. It's not exact because that relies on this symmetry. That assumes isospinetry is exact, and we know isospin symmetry isn't. Heisenberg thought it might be. That's when he said the proton and the neutron are the same particle, and he called it the nucleon. There's just one's just an excited state, the other. But now we know it's not. One's got one more U quark, and the other's got one more D quark. So we take what happens here. We're getting better all the time. And as I say, it's taken 70 years to work out the Hoyle state. I think the first ab initio calculation that showed us it looked like a bent Armand was actually there something like 2011. Fred is suggesting it in 1952. He's guessing it. And we're only just, and that's still a first order approximation, that calculation, based on a thing called an effective field theory we call chiral perturbation theory. But it's all based around these sort of assumptions, and a little bits of guidance we can get from the first order of the real thing, which is the QCD. The QCD we limit with pretending space-time is a lattice, and we do calculations on finite lattices and reduce the size and see if we can guess what will happen when the lattice goes down to 0. These are still very crude. So when you see something involving hadrons, and at the moment we've got people claiming that the magnetic moment of the muon is breaking the standard model. Now, there's terms when you calculate those magnetic muons that involve these approximations. And therefore, one has to be very bloody careful that we're not really testing the standard model. We're testing a model of the standard model, an approximate model of the standard model. And given that it's taken us 70 bloody years to work out Hoyle's guess, When we get to the much more detail of here, this stuff which is way inside the femtometer veil, then we're looking at something much more difficult. And this is what happens when we start speculating about the very early stages of the universe. You know, the very early stages of the universe, the whole universe is within the femtometer veil, everything. And therefore the complexity of that is ginormous. And I'll stop there.